In this lesson, I wanted to show you how different decisions you make about how you present your information can cause an audience to potentially misinterpret what you're trying to show them, or even your own understanding of somebody else's chart or something you read on the internet in the news. So let's first take a look at the small table of data that I've got. For every month throughout the year, I've got an average course rating. So for an educational piece of content, students rate the information at the end of the course, and I've calculated the average course rating each month to see how it's trending. In Excel, obviously, we all know how to make these basic charts, so I'll just quickly pick a chart. And what I'd like to show you is what Excel does by default. So if you take a look on the left here, see how the axis starts at 3.95 and it ends at 4.5? Excel has made a decision for you as to what it thinks the upper and lower limits of your graph should be. Now, unfortunately, this kind of stretches our information because we really only have values from, say, about 4 to 4.5. So it's really stretched apart the differences between the numbers. So if we actually turn on the data labels here, you can see there's not that much difference. So when we view this chart, and the important thing to understand is that when people look at your charts, they draw a conclusion visually first. They don't actually stare at the exact numbers. And so if you're presenting this chart and you're also presenting it without this table, the distance between some of these bars is what people are initially going to see. If we take this and we think about this information in context, this course allows a student to rate the course between 0 and 5. So we really want to set this axis to be representative of that. It can be from 0 to 5. So let's see what happens to our chart now. Now we see that the distance between the height of the bars is so much smaller. So this is more representative of the true amount that these numbers vary over time. When we looked at that first initial chart, there's so much height difference between those bars that visually somebody is going to come in there and think there's actually a more substantial difference than there really is. Now let's take a look at some real-world examples. In a newspaper, and this was from the University of Kentucky, if you take a look at this chart here, so they have actually logged the number of full price sales that the Times had, so 485,720, and their competitor, the Daily Telegraph, so 446,954. Putting those two bars together, look at the relative heights. An audience is going to come along and they're actually going to say, oh my goodness, the Times has twice as many full price sales as the Daily Telegraph. Because we instantly look at that and we judge the height. The one on the left looks like it's at least twice as tall as the one on the right. But let's take a look at how they've done their scale. See how it starts at 420. It does not start at 0. If we actually calculate the difference, how much was the actual real increase between these two numbers? So the Times actually has about 8.7% more full price sales than the Daily Telegraph. But when you look at that chart, would you ever look at that and say, oh, there's really only about an 8.7% difference between those two numbers? It's like we don't do that. We quickly glance and we say, oh, the bar on the left is twice as high as the bar on the right. So let's take a look at another example. So this will be slightly different. And this is about manipulating the axis, the y-axis. So we've got information on the number of defects per million units that are being produced in a manufacturing location. Every year from 2017 to 2021, we've got this number of defects for every 1 million units that come off the production line. So we can see we've got a pretty substantial increase between these 2 years, and then we've got a certain amount of variation after that. Now, we've got our baseline correct because we're plotting down to 0, and we've got it plotting up to about 140. But here's what people do to manipulate the graph. If I format that axis and I say, you know what, let me plot that up to 300, it squashes my line, and now the vertical distance for this increase that we see, which you can see it's more than doubled the number of defects between those 2 years. That increase doesn't look as substantial as it did before. Now, the other thing I see happening, so I'll just put it back to the 140, is that when people take these charts and they want to put a lot of charts onto, say, one single dashboard, maybe you're putting 9 charts per page, I see them plotting it like this. So they squash it to make it fit. But the problem with that is that even though we've got this correct, the baseline is 0, it's got a reasonable number for the top, the actual height of the graph can distort the interpretation as well. So here, if I were to look at that quickly on a dashboard, I would say, oh, well, there's not much difference between the years for 5 years. So very much a difference when you start to change the height or you start to manipulate the y-axis. Now, let's take a look at that same concept. So we had our chart, our defects per million units produced, and we had that jump from 51 to 124. Our chart did 1 year for essentially every tick mark on the x-axis. So I'm not showing the tick marks, but essentially we have 1 year for every segment of the x-axis. So let's take a look at what happens over here. In this particular version, we've got 2017 broken into each quarter, and then we've got all of the full years after that, where we're showing the Q1 value of each year. So what have we essentially done? As we go across the x-axis, the time representation is not equal. So you have to watch out for this. But we essentially are passing, 3 months between each of these, and then we're passing 12 months, 12 months, 12 months, 12 months. So we don't have the same time representation across an equal space on our x-axis. So what does this do? So you can see we still have our value going from 51 to 124, but the horizontal distance over which we've now plotted the difference between those two values is much longer than our initial chart. And that essentially lowers the visual slope, so the angle of this increase that we're looking at when we initially just look at the graph the first time we see it, that slope is lower. So it makes the increase look like it is less dramatic than if we were to plot it correctly and have it once per year. I've seen this in the news. I've seen it in newspaper articles where people are changing the spacing between here, or they're even omitting certain years of information because they're trying to skew the message of the information that they're presenting to you. Just something that you should watch out for, and maybe try to avoid presenting your information on different time zones. Now, there is that case when you're presenting your data where it might be annual for here, and maybe you're plotting 2021 year to date because we're in a partial year, and that's okay. Just make sure that when you're presenting some of the information, so if it's something like a turnover rate, if this is an annual turnover rate, and this is year to date, for an actual comparison, you might want to put the annualized number in here as well, in addition to notating what the actual year to date percentage is. Another thing to look at is unrelated information being plotted on the same graph. So this one's a little bit amusing anyway. So this is the divorce rate in Maine, and it is actually plotting it in relation to the per capita consumption of margarine, of all things. So we know, common sense test, there is no way that consuming more margarine is going to impact the divorce rate in Maine. So this is something that is merely by coincidence, but people tend to put these things together sometimes, putting two pieces of unrelated information together on a chart, because just by placing them together, your audience may instantly infer some sort of connection between the two. Now, this is on a chart. The other thing that I've seen when you're reading articles in the news, reading it online somewhere, watch for paragraphs where people put two sentences together in one paragraph. They are not related to each other, but the fact that you read sentence A immediately followed by sentence B, they've done that positioning to imply in your mind that maybe there's a connection between two pieces of information when there really isn't. Technically, they're not related, but the way they have positioned them in the sentences in their article, they want you to, in your mind, connect these two pieces of information together. What I want to show you in this section is what happens when you start to pick some of the fancier charts in Excel. Well, 3D representations. I'm not sure I'd call them fancier if it's just a pie chart. But if we look at the 2D pie chart, we can clearly see when we look at this that the blue section is slightly bigger than the orange section. So since this represents our cost categories, we can look at this and say, yep, I can tell that the blue section, which is my inventory cost, is a slightly greater percentage of my overall costs than general administration and freight. But if I decide I'm going to present that exact same information, but I'm going to select a 3D pie chart, let's see what happens. So when you quickly look at this chart on the right, can you really tell which is bigger, blue or orange? You can't really tell. They look almost equal. You wouldn't be able to see whether orange was greater than blue or blue is greater than orange. And the reason this is the case is that this front piece, so the orange mostly, is being represented as something closer to you. So it's distorting the actual size of the percentage. So I caution people against using these three-dimensional charts or anything that kind of distorts the actual proportion of something that you're trying to present.